All right, so today we're going to be going through the 2019 AP Calculus BC multiple choice questions. So we have for number 1, let's compute the integral from the bounds of 1 to 2 for 4x cubed minus x. So by using the power rule, we can integrate the integrand. We have the fourth power, 4x to the fourth power divided by 4, and then minus the power rule for x would be x squared divided by 2. And you want to evaluate this from the bounds of 1 through 2. All right, so before we evaluate it, let's simplify the expression. These fours cross out, and we have the fourth power of x minus 1/2 x squared. And let's get this from the bounds of 1 all the way through 2. All right, so this would be the fundamental theory of calculus, which we plug in the top bound of 2 first, and then we take away if you plug in 1 for the function. So we have 2 to the fourth power minus 1/2 of 2 squared. That would be f of b minus f of a, which would be the lower bound. That's 1 to the fourth power minus 1/2 of 1 squared. All right, so now the fourth power of 2 gives you a 16. So that 2 to the fourth power should be a 16. Then minus we have 1/2 of 2 squared. 2 squared is a 4, and 1/2 of 4 gives you a 2. And then we take away from that 1 to the fourth power would be a 1. Then minus we have 1/2 of 1 squared gives you a 1/2. And let's further simplify that. It should be 16 minus 2 gives you a 14. Then minus we have a 1 minus 1/2 would be a 1/2. Now 14 minus 1/2 gives you a 13.5. And that would be the answer, but they want it to be in improper fraction form. And that would be a 27 halves as an improper fraction. And that would be the answer for number 1, which is choice A. All right, so now number 2. Let f be the function defined by f of x is equivalent to x cubed minus 3x squared minus 9x plus 11. At which of the following values of x does f attain a local minimum? All right, so to get the values of x where f of x attains a local minimum, let's first get the first derivative. So f prime of x would be equal to 3x squared for that term. Then we have a minus 6x minus 9. And the derivative of a constant value of 11 would be nothing, 0. And now once we get the derivative, let's get the critical values for the original function. These critical values will tell you where the function goes from increasing to decreasing or vice versa. And wherever the function would go from decreasing to increasing would be a local minimum. So if you set the derivative function equal to 0 to solve for the critical values, then let's solve this equation. 3x squared minus 6x minus 9 is equal to 0. So let's factor out the 3 from every term. 3 times x squared gives us 3x squared. 3 times negative 2x gives us a negative 6x. And 3 times negative 3 gives us that negative 9. All right, so now to solve this quadratic, let's factor the function. And x squared minus 2x minus 3, that factors into x minus 3 times x plus 1. All right, and upon getting the zeros for this equation, we end up getting an x value of 3 or an x value of negative 1. Now, these are going to be the critical values for the original function, and let's perform a science analysis to see where the original function goes from increasing to decreasing or vice versa. So let's make our number line, and on here, let's plot these two critical values of 3 and negative 1. Negative 1 comes first, and then comes our 3. And let's choose some numbers in all of these intervals, which before negative 1, we can choose negative 2. And some number between negative 1 and 3, we can choose 0. Choose convenient numbers in all these bounds. And some number more than 3, we can choose 4 for that. Now we plug in all these numbers in place of every x for the derivative function. And it doesn't matter which step you plug it into, either this derivative function or this one or even this one. It's better if we use this one though, because everything is in factored form. It's going to be easier to tell what the symbol is for the derivative. Now, why we're plugging everything into the derivative is because the derivative is nothing more than slope. So if we plug in all of these test points of negative 2, 0, and 4 in place of the derivative function, it would tell us what the sign is for the derivative. And the derivative is nothing more than slope of the original graph. So we would be able to tell if the graph is decreasing or increasing on all these intervals. So let's plug in first an x value of negative 2. And we don't care about the actual numerical value for it. We just care if the derivative would be positive or negative. So let's plug in -2 for every x in this function over here, the derivative function. So 3, which is positive, and then times we have, if you plug in -2 for the first factor, we have -2 minus 3, which would be -5. And again, we don't care about the magnitude of the number, it's negative. And then -2 plus 1 would give us a negative number. Okay, so now positive times negative is a negative, and negative times negative would be a positive symbol. So upon plugging in -2 for every x, we end up with a positive value. All right, and now let's plug in 0 for every x in the derivative function to see what the symbol is. So 3 is positive, so that's going to be positive, and then times we have, if you plug in 0 for the first factor, we have 0 minus 3 gives us a negative quantity, and then 0 plus 1 gives us a positive quantity. And we know that positive times negative is a negative, and negative times positive would be an overall negative symbol. So the 0 would give us a negative number, and then if you plug in the last value of x of 4, then again 3 would be positive, so that's positive. Then if you plug in 4 for 4 minus 3, that would be a positive quantity. And then if you plug in 4 for the last factor of x plus 1, then that would give you a positive number. All right, so, and all these symbols are positive, and their product will also be positive at the end. So this would give us a positive value, and that means that the original function f of x is increasing up until -1, and then decreasing from -1 to 3, and then it goes back to increasing past the value of 3. And that means that we attain a local minimum at the x value of 3. Again, that would be when the derivative function goes from negative to positive, is when the original function attains a local minimum. And that would be the answer for this. The value of x where the original function attains a local minimum would be x is equal to 3, which is choice A. All right, so that's number 2. Let's move on to number 3. So for number 3, we want to compute the derivative for 2 times a quantity of sine or radical x being squared. And this is nothing more than just the chain rule, right? So now the overall function would be the squared function. So let's first use a power rule to bring the 2 down, and 2 times 2 gives you a 4. So we have 4, and then keep the inner function the same. 4 times sine of radical x. And now the power becomes 1 less than it was before. So 2 minus 1 gives you a 1. Then we have an inner function of sine of radical x, and let's compute its derivative by using the chain rule. The derivative for sine of radical x would be cosine of radical x. And then since we still have some inner function left over, we have to exhaust the inner function. So we get the derivative once again for the inner function, and the derivative for the square root of x would be 1 over twice radical x, if we were to apply the power rule for it. All right, and that completes the entire derivative. So if we write this in a neater way, then we have 4 sine of radical x cos of radical x in the numerator. So 4 sine of radical x, then cosine of radical x, and then we have in the denominator a twice radical x. And the 4 divided by 2 would simplify to 2 over 1, and that would be the most simplified that we can get this derivative to be. So it should be 2 sine radical x cos radical x, and then over at the bottom we have 1 times radical x, which should be choice D. All right, so simply enough. Now we have number 4. The position of a particle is given by the parametric equations. X of t is defined by ln of t squared plus 1, and y of t is defined by e to the 3 minus t. What is the velocity vector at time t is equal to 1? All right, so we're given what the position vectors are, the x direction and the y direction. And let's write that here again. So for the position vector, we're given it to be ln of t squared plus 1. And then we're given the y direction to be e to the power of 3 minus t. Okay, so we know that the velocity vector would be the derivative of the position vector. So let's compute the velocity vector first by getting the derivative of this function for the x and that function for the y. So the derivative for ln of t squared plus 1 would be, again, the chain rule. The general derivative for ln would be 1 over the inner quantity of t squared plus 1. But since we have an inner function of t squared plus 1, let's compute its derivative. And the derivative of t squared plus 1 would be simply just a 2t. Okay, and then for the y direction, the derivative of e raised to any power would be that same function itself, e to the 3 minus t. But we have to use the chain rule because the power is not just t, it's a 3 minus t. So the inner function's derivative, the derivative of 3 is 0, and the derivative of negative 1t would be a negative 1. So let's multiply this by negative 1, which again would be the inner function's derivative. And now let's compute the velocity vector when t is equal to 1, meaning let's plug in 1 for every single t value. So let's compute the velocity at the t value of 1. And so that would be 1 over 1 squared plus 1 times twice 1. And then for the y part, we have e to the power of 3 minus 1. That value times negative 1. Okay, and that becomes, let's see. So at the bottom, we have 1 squared plus 1, which is a 2. So this entire fraction is a 1/2. And that value is a 2 times 1 is a 2. So 1/2 times 2 would be a 1. Okay, and now for the y direction, we have e to the power of 3 minus 1, and that would be e squared. 3 minus 1 is a 2, but then times negative 1, and that would be a negative 1e squared. And that would be the velocity vector at t is equal to 1, which would be choice B. 1 and negative e squared. Okay, so now number 5. So we're given a series, and this is a geometric series. So then you want to get the summation from the first term to the infinity term for e to the n over pi to the n. So if you recall, the formula for the summation of a geometric series, S sub n, to infinity would be equal to a sub 1 over 1 minus r. Right, so this would be the infinite sum of a geometric series if the series converges. Now what the question is that would the series converge? Well, the top and the bottom both have a common power of n, so let's rewrite this as sigma n is equal to 1 all the way through infinity of the quantity of e over pi to the power of n. All right, so now the whatever is within the parentheses would be the common ratio for the geometric series, and that would be this r over here. Now, a geometric series would converge if the absolute value of the r value is less than 1. Now, we know what e is. E is approximately 2.718. And 718, and then we know what pi is, which pi would be approximately 3.14. And now since we have a bigger number in the denominator than we have in the numerator, the ratio of e over pi would be less than 1. And therefore we know by the geometric series test that this series would converge. Now, what should the sum be? Well, we plug it into our formula that S sub n would be equal to a sub 1 over 1 minus r. Now, what's our first term going to be? Let's plug in 1 for every n, right? So we have a sub 1 would be equal to e over pi to the power of 1. And that gives us simply just e over pi. All right, so for the geometric series, we know that the first term, a sub 1, would be an e over pi. And then over at the bottom, we have a 1 minus our common ratio. And that common ratio would be the e over pi that we have over here. So 1 minus e over pi. All right, so, and this is a complex fraction. So to simplify it, let's get rid of all the denominators. Let's multiply the top and the bottom of our fractions by pi. All right, and what that does, that becomes at the top, e over pi times pi. Well, these pi's cross out, and we just have an e left over. At the bottom, we have a pi times 1, which is a pi. And then minus, we have a pi, e over pi times pi. And these pi's cross out, we just have an e left over. And the summation of this geometric series would be e over pi minus e, which corresponds to choice B. All right, that's number 5. Now, number 6, the table above gives values of the twice differentiable functions f and g and their derivatives at x is equal to 2. If h is the function defined by h of x is equal to f prime of x over g of x, what is the value of h prime at 2? All right, so before we get the derivative of h of x at the x value of 2, let's first compute what h prime of x would be. And this would be the quotient rule. So h prime of x. Yeah, so now the quotient rule says there's a rhythm that we can memorize for it. It's low d high minus high d low, and then square the bottom. And that would be the quotient rule. So low means your bottom function, and then d high would be the derivative of the top function, and then high would be again the top function, and then d low would be the derivative of the bottom function, and then the bottom function, which is your low, being squared, and that completes the quotient rule. So if you apply that, then low would be g of x, and then we have d high, so the derivative of the top function, and the derivative of f prime of x would be f double prime of x. And then minus we have high d low, so high would be f prime of x, and then d low would be the derivative of the bottom function of g of x, so that's g prime of x. And then square the bottom, which would be g of x if you square the entire original function. All right, so that completes the general derivative for h prime of x. And now if we want to obtain the value for h prime of 2, let's plug in 2 for every value of x. All right, so this becomes h prime of 2 would be simply just g of 2 times f double prime at 2, then minus f prime at 2 times g prime at 2 over, at the bottom we have g of 2, and that entire quantity being squared. All right, so by looking at the table, g of 2, that would be a negative 2. And then f double prime at 2, let's see, f double prime at 2 would be a 3, so times 3. Then minus we have f prime at 2 is given to be a negative 3, so the quantity of negative 3, and then times g prime at 2, which is given to be a 5. Over at the very bottom, we have g of 2, which is given to be negative 2. And let's square that entire quantity. All right, so that gives us a negative 2 times 3, which is a negative 6. And then we have negative times negative is an overall positive, so plus. And 3 times 5 would be a 15. Over negative 2 quantity squared would be a positive 4. And that leaves us with a negative 6 plus 15, which would be a 9. So 9/4 would be the value for the derivative of h at the x value of 2, which corresponds to choice A. All right, that's number 6. Now we have number 7. So which of the following is the Maclaurin series for x times cosine of x squared? So now let's begin with the Maclaurin series expansion for cosine of x, which should be memorized. So the summation, or rather, let me erase that. All right, so now cosine of x, the Maclaurin series for it is the summation from n is equal to 0 all the way through infinity of negative 1 to the power of n, and then x to the power of 2n divided by the quantity of 2n factorial. All right, so we're looking to get the Maclaurin series expansion for x times cosine of x squared. So let's slowly make this function match the function at hand of x times cos of x squared. The first step would be to change the inner quantity of x from x to x squared. So now cosine of x squared would have the Maclaurin series expansion of, let's replace every x term with an x squared. The sigma from n is equal to 0 up until infinity of negative 1 to the power of n and then times x squared, because we replaced the x with an x squared to the power of 2n. Over at the bottom we have a 2n factorial. All right, so now once we have that down, let's first simplify this. So cosine of the argument of x squared would be sigma from n is equal to 0 all the way through infinity of negative 1 to the n power. And then a power raised to a power would be their product. So Twice 2n gives you x to the power of 4n. Over at the bottom, we have a 2n factorial. All right, so we're almost matched with the function that we're looking for the Maclaurin series for. What's missing is this x. All right, so now to get that, let's multiply both of our sides by x. All right, and that gives us x cosine of x squared would be sigma from n is equal to 0 to infinity of -1 to the power of n. And now we can combine these powers of x's. So x to the 4n power times x to the first power, by using properties of exponents, we can maintain the base of x and we can add the powers up together. So 4n plus 1 would be the new power of x. And then over at the bottom, we have 2n factorial. All right, so now let's just get the first couple of terms for this expansion. We already got the series for it, and let's get the first couple of terms to match it up with one of the choices. So now when n is equal to 1, or rather when n is equal to 0 for the first term, because the series starts off at 0, we have -1 to the 0 power, which is going to be a positive 1, and then times x to the power of 4n plus 1. And since n is 0, that's going to be 4 times 0, which is 0, plus 1 gives you a 1. So x has a power of 1. Over at the bottom, we have 2n, which that's going to be 0 factorial, and that's just going to be a 1. The first term would be simply just an x. I'll put that down here. And then when n is equal to 1, we have -1 to the first power would be a -1, and then times x to the power of 4 times 1 plus 1 would be a 5. Over at the bottom, we have a twice 1 factorial, and 2 factorial would be 2 times 1, which would be a 2. Or I'll just put the 2 factorial down. And that would be the second term in the series. And then when n is equal to 2, we have -1 squared would be a positive 1, and then times x to the power of 4 times 2 plus 1 would be 8 plus 1, and that's going to be a 9th power of x. Over at the bottom, we have twice 2 would be a 4 and factorial. So the first term is x, the second term is a negative x to the 5th power divided by 2 factorial, and the third term would be a positive 1x to the 9th power over 4 factorial. And that matches with, let's see, that matches with choice A. Right, again, so we have x minus the 5th power of x over 2 factorial, and then we have a plus x to the 9th power over 4 factorial, and that would go on with the third term and the fourth term and so on. Okay, so 7 would be A. Let's move on to number 8. So the limit as x approaches infinity for 10 minus 6x squared over 5 plus 3 to the x. Now, if you plug in infinity conceptually using direct substitution, then we see that the limit would be infinity over infinity, which is a form of indeterminate. And upon getting indeterminate for any limit, we can use L'Hopital's rule for limits to infinity, or for any limit that happens to be any form of indeterminate of infinity over infinity or 0 over 0. So to use L'Hopital's rule, let's get the derivative for the numerator and for the denominator. So the limit as x approaches infinity, the derivative of 10 would be 0, and the derivative of -6x squared would be a -12x. Over at the bottom, we have 5 has a derivative of 0, and 3e to the x has a derivative of 3e to the x. Okay, so now from there, if you plug in infinity, then we still end up with infinity over infinity, which is indeterminate, and we can apply L'Hopital's rule once again. So this becomes a limit as x approaches infinity of the top and the bottom derivative. So -12x has a derivative of -12 over 3e to the x. The derivative would still be a 3e to the x. All right, so now we can plug in infinity conceptually, because now we would not end up with indeterminate, and that gives us a -12 over 3e to the power of infinity. And e to some very big number times 3 would be some very big number. So we have -12 over some very big number, and -12 over some very big number would be approaching a value of 0. So the answer for this would be 0, which is choice B. All right, so now number 9, the function f is not differentiable at x is equal to 5. Which of the following statements must be true? All right, so the function f is not differentiable. Let's see which one of these choices would still be true even though the function is not differentiable. A is saying that because the function is not differentiable at x is equal to 5, the function is also not continuous at x is equal to 5. Let me draw a counterexample to that. So if we're given 1, 2, 3, 4, 5, at the x value of 5, the function is not differentiable. Is it necessary that it's not going to be continuous either? Well, if we recall, then a function would not be differentiable if we have any sharp point. So if we're given this type of a graph where we have a sharp point right there, and the curve goes on, we can see that at that x value of 5, the graph is continuous, but it's not going to be differentiable. So just because it's not differentiable does not mean that the graph is not going to be continuous either at that x value. So A is not going to be true. And then B, the limit as x is equal to 5 of f of x does not exist. Well, in the same exact example, when x is equal to 5, the function is not differentiable, but the limit would exist because the left-hand limit and the right-hand limit, they both approach the same number, although you cannot differentiate this graph at that point. So B would not be true. And C, the limit as x approaches 5 for f of x minus f of 5 over x minus 5 does not exist. This would be the alternate definition of a derivative. So the alternate definition of a derivative. And C would be the answer because we're given that the function is not differentiable at the x value of 5. And C is computing what the derivative would be in limit notation when x is equal to 5. So that would not exist because it's not differentiable at that x value. What about D? The integral from 0 to 5 for f of x does not exist. I mean, not necessarily, because we can compute the integral from like the area below the curve from 0 through 5 for this function. So it's not necessary that D would be true just because the function is not differentiable at x is equal to 5. So 9 should be C.